Hello everyone. In this video, we are going to talk about numerical differentiation of data when the data has noise in it. When we talked about numerical differentiation, we said the main motivation is when there is no underlying function and you only have a stream of data. So analytical derivatives that you learn in calculus cannot be used, and you know that many times the data coming from sensors are noisy. They are not perfectly clean data. So what's the problem of applying those forward, backward, central, or those other methods of taking derivatives to some noisy data? As you know, and I mentioned a bunch of times, especially in controls when I talked about PID controller, is noise when taken derivative from will have large magnitudes because derivative gives you the rate of change. And noise is a fast changing signal, so derivative of a noisy signal will be extremely large. Here you can look at this picture. The underlying function is simply a sine of t, okay? So you can see that with the black solid line, it's just sine of t. And I just added a little bit noise to it. So I'm going to show you in MATLAB in a second. I just added a little bit noise to it, so the amplitude of the noise is not really big. The true derivative is just cosine, the red dashed line. Okay, that's what you should get. But here, when I applied the forward derivative to the signal, the sine wave that has a little bit noise, look at this cyan, right? The color cyan. Look at, these are the derivatives of the noisy signal. Look, their magnitude can reach up to 20. Instead of just 1, they can reach up to 20. And that shows that, hey, basically you are really amplifying the magnitude. Look, this is the code. So the function is sine of t, and I added 0.2 rand. Okay, so I added some random white noise to it with amplitude of 0.2, and my y, actual y, is y clean plus noise. And here you see I'm using the forward derivative, and then I'm gonna plot it for you. So I just want to show you the top subplot so you can see the basically limitation of taking derivative from noisy data. So this is that top plot. Now let me focus on a portion of it so you can see what's going on. You see, so this, the dotted blue line, this one, this is your noise added to your underlying function, right? And clearly you see that the amplitude of the noise is not really big, right? So if I just plot for you the y only, right, just the y, you can see that the noisy signal, look, this is my noisy signal. Okay, you clearly can see sine wave, but with a little bit noise added to it. And when you take derivative of this, you get those big signals. So how can I avoid that if I want to do it numerically? So the first way is we first smoothen the data by a low-pass filter that removes the high-frequency components. And then we apply a kernel that can do the derivative, like forward, central, or any other kernel. And we can use convolution to perform the derivative numerically. And there are lots of different ways to smoothen the signal with a low pass filter, right? So this is a low pass filter and this is the derivative filter. And when I combine these two together, what I will get is basically a high pass filter. So the goal of that high pass filter should be to smoothen the signal so the noise is not amplified by derivative, but at the same time, you don't want to over smoothen the signal so the main features and characteristics of the signals, main transitions and so on, still remain. So one of the filters that is very common is, we call it the running average or the moving average filter, right? And basically, so if you have a bunch of numbers, basically, so let's say 1, 2, 6, 9, 3, 6, 3, and so on, and 7. So if you put a filter of length 3, so it goes here and take the average of them and then replace the middle of the filter, the center of the filter, with the average of them, right? So this is like 9, the average is 3. then it moves 1 unit to the right, and then again takes the average of them. So that is like 17. So that is going to be 17 over 3, and so on and so forth, right? And when it's in this beginning point, right? So when you want to know what happens here, so if it's like this, you want to replace that. You don't have any data, you do padding. So you can either do mirror and put this 1 on this side with respect to the borders of the signal, or you can pad it with zeros. So if you do that, now you're going to get the 1 here and keep going. So this is the moving average, which over smoothened the signal many times. So instead of giving all of these guys, all of these numbers the same weight, which is in this case is 1/3, because the length of the window is 3. One other thing you can do is to use a Gaussian kernel, which puts more weight on the center and less weight on the signals away from the center. This way it preserves the transitions better. And you know, the Gaussian kernel, the formula for it in 1D is like this, and in 2D it's like x squared plus y squared. So for instance, if you have a 5x1 kernel, right, and the sigma that you use is 1, which controls the spread of the data, then look what happens. So for sigma 1 and 5x1, these are the numbers that you have, okay? And you clearly sum them up. The sum is equal to 1. And one of the other things that you always know is that the length of the signal, the size, the window size, should always be an odd number, okay? Because you want to have a center for it. So you typically do not use a filter that is like 2x1 or 4x1 or something. You always use a 3x1, 5x1 or something like that. So that is the smoothing part. Now, if you combine that with a derivative, so you want to perform a derivative after that, one thing you can do is, instead of having one kernel for Gaussian and then another kernel for the derivative, right? For instance, for the forward, right? It's the next data minus previous, the next data minus current data, right? Or if it's central, if it's the next data minus previous data. So it should be something like this H, but since in convolution you flip the signal, actually this should be 1, this should be -1, right? And then you can combine these two filters to get the central version of the Gaussian. Another way to do it is you perform the derivative analytically on the Gaussian. So you take a derivative of this with respect to x, and you get the derivative of the Gaussian filter, or DoG filter, which is like this guy. And then you plug in some sigma and some length for x and get number. This way, this has both of them. So already this DoG is your high pass filter. Okay, and here for a sigma of 1 and again a 5x1 kernel, you can see this is your DoG filter, and once you apply that to the signal by convolution, that does both of the jobs, smoothing and taking derivative. Okay, so you can just use a convolution of the signal with the DoG. So this is one method to do it. And if you don't like the Gaussian, you want to use another smoothing, again, if you can analytically take derivative of that, that's much better. If not, then you can basically put those two kernels together back to back. Now, what is the role of sigma if we use DoG, which is one of the best ones? Sigma, of course, controls the smoothing of the signal. The bigger the sigma you use, the more smoothened the signal is going to be, and it will amplify the noise far less. So if the signal is very noisy, you have to use big sigma. If the signal is relatively clean, use a smaller sigma. Otherwise, you will over smoothen the signal. Okay, so the more noise, basically, the bigger the sigma that you want to choose. Okay, of course, picking the sigma is a little bit tricky, and we're going to talk about it at the end of this video, but this is the first method that we can do. The second method is called the Savitzky-Golay filter, and this is again one of the so many methods for performing numerical derivative of noisy signals. And this one is very interesting too. How does this one do it? So this one first fits a local polynomial. It could be any order, second order, third order, anything, to a moving window on the data. So first it does some curve fitting and finds a function that fits a few data inside the window. Then, since it's a polynomial, now you can take your derivative analytically. Okay? And if I want to show you that in a picture first, before we get into the formulas of that, let me show you how it works. This picture is coming from Wikipedia. So the way it works is, here, consider the cyan data is your noisy signal, okay? And the moving window has this size, okay? So that is the length or the size of the moving window. So right now, if you only look at the data in this cyan curve within that window, you fit a polynomial to it of whatever order that you like. Here, for instance, the polynomial was order 4, and the length of that window was 45 data points. So to 45 data points, you fit a fourth order polynomial. Of course, the order is way less than the number of data points, so you have to do it with the least squares method. And this guy here in red, this kind of W shape in red, is the fitted polynomial. Okay, and once you have the fitted polynomial, guess what? You can take derivative of this fitted polynomial. Now, of course, you can see that the fitted polynomial and the actual data are quite a bit different, right? So this is the actual data, and this is the fitted polynomial. It preserves the overall up and down nature of the signal, but you can see this W is much sharper than that one. So of course, this one has limitations as well, and we're going to see that. But this is another way to take advantage of taking derivatives. Now, this method works great when your data, when the independent variable are equally spaced. When that's equally spaced, then we use the least squares, as I said, and we can find simple and nice analytical solutions to the problem. How? So let's take a look at the formulation. And again, this part, the material is coming from the same Wikipedia page. Okay, so this page here, I got these formulas from that part as well. So let's say, in general, you have n data points, x and y. This is the total length of your signal. So let's say you have 1,000 data points, okay? Then you're gonna go and pick a window size of size m. And it should be an odd number. So let's say m is 5, 11, 41, or anything you want. So you pick some size for the window. Remember, in this case, look, it's 45. And to every 45 data, starting from the left side of the signal to the right side, or smallest to the largest, you keep fitting a polynomial to these m data points. What is the polynomial that you fit? It is going to be of order k. K is a parameter that you pick, it's a hyperparameter that you pick, as well as m. Both of these are the parameters that you have to pick. And of course, they would affect the final results. Now, before you take these x and y data, mx and y pairs, and fit them a polynomial, you do a change of variable, you do a normalization, then you fit the data, which is much easier. So first, if the step size is constant between your data points and is equal to constant h, you subtract each data point from their average for x variable, independent variable, and divide them by the step size, and you create this z variable. Now, z variable is, of course, if your data are equally spaced, once you calculate z, the z is going to be like from 1 minus m over 2 all the way to 0 to m minus 1 over 2. And you might say, how come? So let me show you something simple. So the first data, let's say, is x naught, correct? The second data is x naught plus h right? And then let's say you have m data points and m is an odd number. So let's say m, just for simplicity here, m equals 5. So the next data is x naught plus 2h, and then you have x naught plus 3h and x naught plus 4h, right? The data are equally spaced. Clearly, this data here is your average. So when I subtract that data from the average, which is itself, and divide by h, this one, the z-score for it is going to be 0. What about this guy? So if I subtract this x naught from that, you get 2h divided by h, you get a 2. For this one, you get 1h, correct, and negative 2, of course. You get negative h divided by that, you get negative 1 here, you get positive 1 here, you get positive 2. And is that the case here? Yes, because this is 1 minus 5 divided by 2, and this is 5 minus 1 divided by 2. Okay, so your data are going to be a bunch of integer numbers from 1 minus m over 2 to m minus 1 over 2. And now, to this set of integer z values, you fit your y data. Okay, so you don't fit y to x, you fit y to the transform version of x, which is z, a bunch of integers. And you fit a polynomial of order k. The question is, what are these constants, a naught, a1, all the way to ak? And you know, since m is much bigger than k, you have to use a least squares solution. And the least square solution, as you know, is basically the pseudo inverse of the J matrix times the values y's. Now, what is the J matrix? J matrix is what we call the Vandermonde matrix. And the first column of it is all ones, the second column are the data, the third column are power 2, all the way to power k minus 1. Okay, I found there was a typo in there, so it's all the way to power k minus 1. For instance, again, if you have a cubic polynomial, so k equals 3, and you have 5 data points in your window, m is 5, this is your J matrix, right? So 1's, z's, z to the power 2, z to the power 3. And if you plug these j's into this J matrix here and consider this y to be from yi minus 2 to yi plus 2, and plug it here and solve for it, the coefficients a's, a0j, 1j, 2j, and 3j, the 4 coefficients of the cubic polynomial, are given based on the y's that you have. Okay, so these guys are y of basically j minus 2, y of j minus 1, y of j plus 1, and y of j plus 2, okay? And your coefficients are a naught, a1, a2, and a3. Why do we use a j here? Because as your window moves, your y's will move and your z's will move. Now, if the window is size 5, the good thing about it is, and the data are equally spaced, the j's do not change really. Okay, because your z is always going to stay at these 5 numbers, so that's the good part. The j will never change, only y will change, and so these formulas can be valid as long as you replace these y numbers in them. You get the a's for that window, and once you go to the next window, the y's will change, the a's will change. Okay, so this is your cubic polynomial, right? And now that you got it, your polynomial, remember, is something like that. Good. So now, what are the things that you need? So remember, you have your polynomial. Now you need to do a first derivative, for instance. So if you want to do a first derivative, then all you need is to take a derivative from this, and the derivative from this with respect to the x. So this is y with respect to x, but y is a function of z. So here you have to use a chain rule. So d of y with respect to x is d of y with respect to z times d of z with respect to x. Now d of y with respect to z, clearly you see that's a1 plus 2a2z plus 3a3z squared. And derivative of z with respect to x, if we go up and look at this transformation, it's simply 1 over h, correct? So This guy is simply 1 over h, and that's what you can see here. Now remember, we always calculate the values at the center of the filter, and center of the filter is where z equals 0 or x equals x bar. So here I plug in z of 0, and guess what? I simply get a1 over h. So as I move this filter, cubic filter of length 5 over the signal, all I need to do at each point is to replace that number with what? With a1 over h. H is the step size, and a1 basically comes from this number here. This is your a1. Okay, so what you need is to basically replace them with this number just divided by h. So you need the y2 behind, 1 behind, 1 forward, 2 afterwards. Do this formula, 1 over 12 and h. So let me write it 1 second. So your derivative will be 1 over 12 times h, and then yj minus 2 minus 8 times yj minus 1 plus 8 times yj plus 1, and then minus yj plus 2. Okay? And here I have a very important question for you. Have you seen this guy anywhere? Yes, you did. This is the 4, or you might call it the 5-point formula that we have for the first derivative, right? If you watched my previous videos, look at that. That's exactly this one. Look, that's this 4-point difference formula. So do you see? This filter exactly gives you the same formula as the 4-point difference if you are using a cubic polynomial and a 5-point filter. Now, of course, if you use a larger filter, you're going to get a different formula. But this here gave you actually the same result as that. Okay, so something interesting to look at. Right, so this is how this Savitzky-Golay or SG filter does. And in MATLAB, there is a command for that you just need to pass to it m and k, and it will perform the derivative for you. So now let's first look at the result of it in MATLAB. So here is the result, and I'm going to run the code for you. This is the same sine wave that I have with some noise. Now, I didn't show the noisy signal here. I just showed the true derivative of that sine wave, which is this red line. And the Gaussian DoG filter, the DoG is this black guy, and the SG filter is the blue guy. And as you can see, the DoG does a much better job compared to the SG, right? You see that SG still has some noise in it, but the DoG does not. And the DoG magnitude and the SG magnitude are similar to the signal, but there is a phase shift. Clearly, SG has a big phase shift, about pi, falling behind. And also, as I said, it did not completely remove noise. The good thing is the amplitude of it is similar to the cosine of t. The amplitude is about 1. Okay, but it did not do as good as the DoG did. Okay, and if you want to get better results here, you probably need to change the length of the filter and the order of the polynomial. So let me show you the code here. So this is the code. This is the DoG that I applied with a sigma of 0.3. And for the SG derivative, the window size is 91. So I used big because if you don't, the noise is barely going to be suppressed. It has to be relatively large because this white random noise is a very fast changing signal. And the order, I used order 3 to avoid overfitting. But again, you can change this and make it basically bigger. And so the command that is used in MATLAB is sgolay, okay, right, or sgolay. So you just pass to it order and window, and it will give you the coefficients for it. And once you have the coefficients, now to apply that, you need to first create the filter and then apply it to the signal with convolution, and same to give you the same length. Now look, the way that the filter is made using the coefficients is here you use the command factorial, and then you pass to it the derivative order. So you just want to calculate the first derivative here. So you just do factorial of 1 divided by dt times g of, and then all the rows and derivative plus 1. Okay, so g is basically those coefficients that you have, and once you have that, you don't use b, you just use g, and that one will give you the filter, and now you can use the filter. And if you are wondering what is b, you can always go to MATLAB syntax and look at the outputs of this function. So as you can see, the b is the filter, okay? But if you want to have different orders for the derivative, because remember, once you have the polynomial, not only you can get the first derivative of that polynomial, you can get second and third derivative if it's order 3. If it's higher order, you can even go for further derivatives, right? And that is one of the advantages of this filter, is not only it gives you the filter for the first derivative, it gives you the one for higher. So the second derivative of y with respect to x is going to be this guy, and if it's calculated at z of 0, it's simply 2 over h squared, and the third one is simply 6 over h cubed times a3. So once you calculate those a's, you can have higher order derivatives as well. So here in this code, g basically can give you the ones for higher order derivatives. And in this case, I don't really need it. I just need first order derivative. But the way that the code is written, you can get any derivative that you like. And here, I'm just using the first derivative here. Okay, and we are going to apply that here. And we are going to show the result. For instance, in this example that you can see, there is a sine wave with noise. And then for orders of derivative from basically 0 to 3, look here, p of 0 to 3. So the first derivative is p plus 1, so it's the first derivative. And you see it is coming from g. And look here, this is the noisy signal in blue. And then you have the smoothened version of the signal x. And then you have the first, second, and the third derivative. Okay, do you see that? So, and you might say, what is 0 used for? Okay, what is 0 used for? 0 is just the fitted signal, the fitted polynomial. It's not even any derivative. So not only this method can give you the derivatives, of course, since you have the a's, it gives you the fitted polynomial without the derivative. So it's going to be this x that you see in red is a bunch of cubic polynomials, patches of cubic polynomials that are attached together. So it's basically like a cubic spline or something. Okay, now there is no guarantee of smoothness and everything, but clearly it's just a bunch of cubic polynomials attached together. And then using that, you can calculate first, second, and third derivative. So this SG filter can give you lots of data points, lots of curves, which is really good. Okay, that is the power of this SG method. But as you just saw, when I ran the code, it did not do that great of a job, right? So look here. First of all, you see it did not completely remove the noise. And second of all, you see that there is a phase shift with respect to the actual derivative. So you might say, go back and change some of these numbers. For instance, make the order a little bit higher. So I don't know, make it like order 9 or something, and see if it makes much of a difference. So let's take a look here, see what happens. So look here. Now you see, actually, it got a little bit worse. The phase shift got a little bit better or maybe the same, but it got worse because we are really doing overfitting. So it's not a good idea to use higher orders. It's better to go back to lower orders. And you might say, what if we change a smaller window size? So make this 31. Look what happens. Again, you see that it is actually not removing the noise so nicely. So it's better to go with shorter order polynomials but bigger window sizes. So if I make this like 121 or 151 or something, you probably might get something a little bit smoother. Look here. You see, actually you remove the noise good. There is a really good removal of noise. Of course, again, there is a phase shift, which I'm going to talk next. So that is a drawback of these methods. So let's go back and talk about the important thing. So when we are using these filters and we are convolving, whether it's DoG or SG filter or anything, remember we are really dealing with an FIR, right, filter. And basically, you know that they have some magnitude and they have some phase. So their magnitude and phase, if they are not one magnitude and phase of 0, they will definitely distort the signal, right? Because the signal Y goes in, this FIR filter acts like a physical system, and the Y filter that comes out, that will have an altered magnitude and altered phase based on the magnitude and phase of the filter that exists for the different frequencies in Y. So if you are wondering what kind of shape does the filter magnitude and response have, here I have this extra part for you. And here we do basically use the command fric_z to see the frequency response. And these are the frequency responses of these curves. So the blue one is the SG filter and the black one is the DoG filter. This is their magnitude, this is their phase. And you see that the magnitude in decibels should be around 0. Once it's 0, that means the magnitude is 1. It doesn't alter, but you see it's a little bit below, it's a little bit negative. And negative means the magnitude of output will be a little bit less than the input. And clearly you see that the phase in radian, which should be 0, is not exactly 0. It's quite a bit below 0, as you can see here. So they have really, I would say, magnitudes close to 1 and phase close to 0 once the input frequency is close to 0 as well. Okay, once you have small varying signals, yes. But for the sine function itself, that frequency is 1, so that does actually a relatively good job. But this noise has bigger frequency. Now you might wonder, what happens if I make this 10 times t? If I make this 10 times t, what's going to happen? I use a higher frequency for the signal, and I have to also change the basically the true derivative and run it. And let's take a look, see what happens. There we go. Seems like I didn't do it in the second one. Need to absolutely do it in the second one as well. Okay, there we go. So look. Now, here you can see something interesting. That the SG filter here does a great job, but the DoG doesn't do a great job. Do you see that? This time the DoG is absolutely not doing a good job. The magnitude is reduced big time. Okay, but the SG is actually doing a relatively good job. And again, you can see that the actual derivative without doing any filter is showing huge magnitudes up to like 25 or something. So we definitely want to apply a filter. Which filter? Here you can see that for bigger frequency, I definitely can get along with the same SG filter that I had last time, but the Gaussian one did not do a good job, and that means I have to go back to the Gaussian filter, and I need to change the sigma, right? So this time my data is faster. So let's see if I change this from 0.3 to, let's say, 3, right? What difference would that make? And you see, actually, it made it extremely worse because you are increasing the sigma while the frequency is going up. So instead of 0.3, I make it 0.03, make it 10 times smaller. And let's see. Now look, now it's much bigger. So you can see that with the DoG, the selection of sigma is relatively tricky, okay? And different sigmas can give you clearly different results, right? So you have to be really having a good idea of what kind of sigma you are picking. You see, I'm getting a little bit better, but absolutely, again, not super great. So you can try that, but again, this is the tricky part. Now you see I'm getting close to it. But you see that the SG actually did a good job here, although I didn't change anything but made the signal much faster. So if I want to compare them at the end of the day, I can say in terms of the noise suppression, DoG does a very good job. The SG is not as good unless the size of the window is relatively large. In terms of feature preservation, the SG does a better job, especially when the signal gets faster. In terms of parameter tuning, DoG has a tricky part, which is tuning sigma. For SG, picking the window size and polynomial is a little bit more intuitive. You see that polynomial order should not really be large, and window, the bigger you pick it, the more noise suppression you will get. And you see that both of them have basically these ripples in their frequency response, right? So you can see all of these ripples here. And in terms of edge handling, so basically here, since you have a Gaussian with tails truncated, you can handle that. And here, edge distortion if window overlap boundary, and this is something that you saw in that graph. Let me do it again so you can see the SG does a great job, but not close to the edges. So you see here, when I'm close to the edges, look, the SG and the true derivative are now quite a bit different from each other. In the middle, SG and the actual derivative are really close, but close to the edges, it doesn't do a super great job. And finally, in terms of computation, this is very efficient, especially because it can give you several extra derivatives if you want. And this is a little bit more costly when the kernel size is large. Okay, so again, SG does need a bunch of computation, but if you need more than one derivative, that could be relatively efficient. So hopefully this video was useful to you. You learned something, how to take numerical derivatives of noisy data, and I will share this MATLAB file with you under video file description, and I'll see you in the next lecture. Thank you.